Hello. I have been in the computer industry for 50 years this year. I've been programming for 50 years. And about 25 years ago, I met Linus Torvalds and saw Linux for the first time. And I said, this is really something. This is more than just a hobbyist operating system or a technical operating system. This has real value, real commercial value to the industry. And so I started working with Linux. I gave Linus Torvalds his first 64-bit computer. I developed an engineering staff inside of Digital Equipment Corporation to help put Linux onto the Alpha processor. I also wanted Linus to make his source code tree so that it could support multiple architectures, not just CISC architectures like Intel or AMD, but RISC architectures such as PowerPC, ARM, and others. Then in 1995, I assumed the executive director role for an organization called Linux International. And while a lot of organizations were functioning on the technical side of the product, we were focused on the business side of the product, trying to get standards for binary distributions out, trying to create a process of creating open source professionals, certified people who could help industry maintain their computer systems. We worked to create the Linux standard base. We protected the Linux trademark for anybody that wants to use it for any purpose. And we promoted Linux worldwide. In 1994, I made my first trip to Latin America. I went to Caracas, Venezuela, pre-Chavez. And in 1996, I came to Sao Paulo, Brazil. I saw the University of Sao Paulo with 100,000 students and 16,000 PhDs. I saw the first Beowulf supercomputer I had ever seen in real life working at the university. And I began to realize the amount of knowledge and skill and intelligence that is in the Latin American community. You know, I come from a very strange country, I really do, called the United States. And we have, when we think of Latin America, we typically think of it in a bad way, or we think of the Brazilian rainforest, or we think of piranha, or football, or carnival, but we don't think that Sao Paulo is the second largest city in the Western Hemisphere after only Mexico City, with New York being third. So after many, many trips to Latin America, I started to see ways I think I could have helped out. For example, I helped to bring some of the first exams for the Linux Professional Institute to Brazil and administer those exams. I started a project in 2005 called Project Kawan. You'll hear more about that tomorrow in a different talk. But the function of that talk, the function of that project, is to create jobs for people in Latin America and to help university students make more money and be able to get a university education. And then in 2011, I helped to start the Canitas Lucas project, which is creating small, inexpensive computers here in Latin America. And again, you'll hear more about those tomorrow. If you put all of these things together, we're at a critical point in open source technology where we can create what I call the Grand Slam, where everything is lined up, and all we need is that little bit of catalyst to turn it on. I am the board chair for the Linux Professional Institute. We have 150,000 trained professionals around the world in 180 different countries. There are some countries we cannot go to, unfortunately, like Cuba, but we're trying. And then there's other countries like Iran that I would like to go there too, because I don't believe the Iranian government is the essence of the Iranian people. This is the 20th anniversary of LPI, and we are about to become a membership-oriented organization. In other words, the people that have the certifications are the ones who drive the certification market, not a small group of people or a small group of companies. And who are you? I recognized in 1994 and 1996 that you are entrepreneurial people, that you can do amazing things. You were one of the largest users of open source software. You had major open source events like Feastly or LatinoWare or others. And you represented a bunch of other countries like Argentina, Uruguay, Colombia, and others. And you are the future leaders of your country. No matter who you elect, it's you. So, over the years, I saw a lot of different things happening, and people told me different things. They said, CPUs are fast enough. Now, like I said, I've been programming for 50 years. I've been hearing that for 50 years. Isn't this fast? Isn't this wonderful? Yeah, okay. Tell me more. CPUs will never be fast enough. Memories will never be large enough. Storage will never be great enough until I can talk to my computer and have it understand me at least as well as you are understanding me now. Java is the only language we need. We don't need to know assembly language. We don't need to know anything else. Quite honestly, Java is a very nice language, specifically if you're using it in the correct way. You could have it on your device, here in your hand, but back on your server, you may not want Java. And I will believe that Java is the only be-all, end-all language when Larry Ellison rewrites the Oracle database engine in Java. But he won't. Nobody codes in assembly language anymore. Well, thank God, I coded in assembly language for 7 years in the beginning of my work. And I don't want to do that anymore. It's problem-oriented, it is slow. However, it gave me an understanding of how computers worked that when I coded in an upper-level language, I would think about that. And that allowed me to write programs that were much more efficient, much more performance-oriented than somebody that did not know that. And I've had professors tell me virtual machines make architecture knowledge unimportant because it separates you from the actual architecture of the machine underneath. And I think these people have virtual machine confused with emulator. Because in most virtual machines, when you're actually running user-level code, you're actually running on the hardware itself. And only when you do something which is outside of that virtual machine do you create the emulation of the operating system, not necessarily the hardware. And in all of these things, you have to have this balance of what is your time worth versus what is the machine's time worth versus what's your customer's time worth. And we'll see more about that in a moment. When I started programming in 1969, my job was not to write new programs. My job was to take other people's programs and make them run faster. That's why Aetna Life and Casualty, a large insurance company in Hartford, Connecticut, hired me. I had been programming at that time for about 3 or 4 years in assembly language, and they said, we need somebody to help us take these programs written in COBOL, running on these IBM mainframes, to run faster, because they're taking up too much time. They're taking up too much of the machine. And so I would go along and I would look at the programs and profile them, see why they were running slow, and change sometimes just a little bit of the program, and magically it would run in 1/3 the time, or 1/10 the time. Or in one specific case, 1/2000th of the time. The same machine, the same operating system, written in the same language, reduced from 10½ hours to 3 minutes. And it's because I understood how the machine worked and could apply that understanding to the problem itself. Now, today, we say, oh, gee, CPUs are really fast and everything, and we don't have to worry about that as much. But we still do. Because if you're programming in real time, and real time meaning that you can get the solution back in the time frame that makes a difference, that's real time. No matter what other definition of real time you've ever heard, that is the definition. That you're guaranteed the answer back in the time where you actually need it. If your nuclear power plant is melting, then the time that you need that answer back is to lower the rods fast enough that it doesn't escape into the atmosphere. If, as in the days of Alan Turing at Bletchley Park, you're trying to decode the Germans' messages, real time is getting that decoded message back before the German U-boats attacked the ships. Right? Typically 1 day. That was real time for the Bletchley Code breakers. And so you need to be able to figure out what the time is to do this and how are you going to do that. Another way of looking at performance, and this is much more of today, is how long is my battery going to last? I had an application on my cell phone one time. It was written by a company that the application helped you to find the nearest hotspot for them. And I started to run that application, and I noticed that all of a sudden my cell phone battery life went from close to 2 days to 1 hour. And I immediately took that thing off, and then my cell phone battery life went back to 2 days again. And so performance in their case was, how can I write my application so it doesn't drain the battery? How can I run my application so that solar power will be good enough to power my server system? Speaking of server systems, Google has large server farms. Oracle has large server farms. And we take a look at that. Maybe they have 10,000 machines. And if you could make your application only 10% more efficient, maybe they only need 9,000 machines. And maybe they can then save a lot of electricity. They can save a lot of air conditioning and still get their jobs done. And so performance these days is not just measured in how fast the program gets finished, but in how efficient it is in getting that job done. We should also, as programmers, start looking at some interesting technologies coming out. There's a thing called a field programmable gate array, an FPGA, which basically is a large group of transistors and other types of circuitry put on a chip, and you can program the chip to actually create new circuits inside of the FPGA. The Mars rover that recently stopped working after over 20 years of being up there crawling around on Mars only had 2 Intel 386 processors in it. It was designed long enough ago that the Intel 386 processor was state-of-the-art. And they had 2 of them in there in case one of them failed. So most of the time, the Mars rover was using one Intel 386 processor to crawl around on Mars. However, every once in a while, we would take a photograph. And if the Intel processor had to compress that photograph, it would take a long time. So they also had 40 field programmable gate arrays on that Mars rover. And when they took that picture, they would turn on the field programmable gate array, and it would go compress and send that frame or that picture back to NASA. and then turn off the field programmable gate array so it wasn't using any more power. And this is the way they did a lot of their programming because the 386 was simply too slow. Now, I was actually programming the equivalent of field programmable gate arrays in 1969. However, they cost $2.5 billion and would take up something the size of this room. And that was a little bit inefficient to try and wear on your wrist. But today, these field programmable gate arrays can fit on the head of a pin. And they cost maybe $21 US dollars. And that's in today's dollars. So these have the same capability of sometimes running applications 100 times faster and more efficient than a regular CPU. And we should be looking at these things to act as accelerators of our applications. If you're looking for something new to learn how to program an FPGA. And I guarantee you, sometime in the near future, you're going to find a real need for your expertise. This was the second computer I ever programmed, a PDP-8 computer, very simple. It only had one general purpose register, and everything went through that, including your I/O. It didn't have DMA, as we know it. It had a stack pointer. Oh, yes, somebody brought up some paper tape that went on the ASR33 teletype right there, which read this paper tape at the rate of 5 characters a second. And the character was somewhat smaller than a byte at the time. And so think about it. If your program is 3,000 characters long, and you want to punch it out on that teletype, well, divide 3,000 by 5, and you find out it takes over 60 minutes to type it out. No, 60 seconds. Sometime. It's long. It's long, okay. And it only had 4,000 words of memory, each word being 12 bits long. And this is the machine that I first learned assembly language on. I had learned Fortran on a previous computer, punching on cards, but this was the second one I ever learned on. And nobody ever bothered to tell me that assembly language was hard. I just read a book and I learned it. And you can too. And I understood at that time that in order to write really great code, you really need to understand how the computer works. And why is that? Well, first of all, what happens when the compiler makes a mistake? That really happened a lot back in the days of 1969 to 73. You would get a new compiler written by some company, and you would, it would compile programs to a certain extent, but then, as you turned on the optimization, sometimes things went crazy, and it wouldn't produce the right code. And you could look at your source code the entire day, the entire week, the entire month, and not see what the problem was, unless you could generate the assembly language and look at it. There were certain instructions aside of the IBM, and there were certain instructions aside of Intel or any CISC computer, and even RISC computers, that take different amounts of time to work. They're innocent-looking instructions. Oh, a string search or something like that. But when you start looking at the instruction itself, it takes a long time. And if you could substitute some other instruction or set of instructions for that, you might be able to improve the speed of your program dramatically. But if you don't know that it's that instruction that the compiler is generating, you don't have an idea about what to do. Cache. Cache on various chips. There's sometimes on a server system, there's lots of cache, and sometimes on tiny little chips, there's not much cache. But the more you can keep of your data and your instructions in that cache, much faster will your program go. And it was this rationalization that allowed me to speed up that one program 220 times. Tapes. I love tapes. There are start-stops tapes and there are streaming tapes. Well, let me tell you, if you can't keep those tapes streaming, they are slower than molasses on a cold day. And so any type of device, whether it's flash, even RAM, if you can figure out how to move your data closer into the registers of the computer, you will see dramatic speed-ups and dramatic savings in electricity. So today, unfortunately, some students in universities are learning things that I just don't agree with. They're learning Microsoft Office and Oracle instead of how to use an Office system to do your work and how to use databases. Now, I have no objection whatsoever in teaching Oracle as an example of a database. That's fine. But you need to know the rest of the stuff, even if you're going to be using just Oracle. You need to understand how the database works, and you need to understand how to tune it to make it faster. They're learning Java and information technology instead of assembly language and operating systems. You need to at least understand what the operating system is about and have the experience and the ability to work on real iron, maybe even build real electrical circuits in your university. I ran into a friend of mine. I have a lot of respect for this person. He's very intelligent. He's starting to get more into the hardware aspects. And he couldn't understand how a software program could turn off the electricity inside of a CPU. He said, "You mean the program running on a CPU can actually turn off other sections of the CPU?" I said, "Yes." He says, "How is that possible?" I says, "Because you're telling a transistor inside the CPU to act as what we call a gate. It's just like slamming the gate in your garden or slamming the door in your house to turn off the electricity, and then later on you tell it to turn it back on again." And he had a hard time understanding this. I'm going to have to spend some time with him. So he does. And what we found was that the students of today are going to the store and buying a laptop computer, which somewhere on the laptop has that label that says, "If you open this laptop, you will void your warranty." And then they buy a game, and they put it on the computer, and they write some HTML for the web page and say, "I am a programmer." I'm sorry, you're not. These are the way that most high school students see computers, and this is the way they really are. They are not friendly. They know you're out there, and they hate your guts. And they're just waiting to trick you into the complacency that your program's going to work. Some simple things like holding a number. You put in your high-level language, I want you to have this number, and this is the way you're supposed to be holding it, whether it's an ASCII number or what is known as a packed decimal number or a straight binary number. Is it little Indian, where one end is the most significant bit, or big Indian, the other is big? How are you holding your data? Because that means that when you start to use that number as an index into your array, it has to be converted from holding it that way into how it's going to be used as an index. And that's a problem, because if you're asking that to be done millions and millions of times a second, then you may not be holding it the right way. I have this is my mug in a mug place in Redwood City. They had mugs from 1 to 135. And I said, "I want mug number 0. because all good programmers start counting from 0. And when the Uruguayan Linux users group started up, they said, oh, we want you to have a badge for us. Okay, make me number 0. I'm proud of that. And the professors at the University of Cambridge in England saw this problem. They saw that the students coming into their university knew less about computers than the ones of 20 years before. The ones who were using the Enigma and other things where you would pull down the source code off of bulletin boards, get it to compile on your system, and have these things called syntax errors and runtime errors that today, when people see them, they just call up the manufacturer and say, I'm having this problem, fix it. And they don't even know how to describe the problem. And that is why the professors at the University of Cambridge developed the Raspberry Pi, purposely not having a case on it, purposely forcing people to use this obscure operating system called Linux, or GNU Linux, to make Richard happier. And from that, there's been a whole series of these little boards which all have different capabilities that are really fascinating. One of them has what we call the big little thing, where there's 2 CPUs on it. Each one has 4 cores, and one runs slower but uses a lot less electricity, and one runs faster but uses more electricity. So most of the time, your operating system and your programs run down here in the slower computer, and the faster one is turned off. And then as the load builds, you turn on the faster computer and migrate, the operating system migrates your applications to it, so you can get your programs back in the time you need them. So we tried desperately to get the Raspberry Pi people to allow us to manufacture Raspberry Pis in Brazil, lowering the cost from the street price of $150 down closer to what they should be, say $40 or so. And after 2 years of working with them, they said no. So we took a different path, and at the University of Sao Paulo, I've been working with the Professor Sufo and a group of students there to create a computer that we can design and manufacture here in Brazil. This has actually become part of what the Brazilian government calls the Internet of Things program. I'll be talking more about this tomorrow. But this allows you to do some interesting things, like build this, which is a supercomputer in a briefcase. I built this originally using ARM units called the Banana Pro, but as we bring out the Labrador in the next month, I'm going to be switching it over to using the Labrador to build this. And why is this important? Because I can take this various places, in a matter of minutes assemble it, and teach things like parallel programming, like a Beowulf system, high-performance computing system. I can teach heterogeneous programming by putting different operating systems on each one of the computers. I can teach systems administration of heterogeneous systems. I can teach high availability programming, with one system failing, the other system taking over. There's many different things I can teach, and I want to get the price down so that it's only perhaps under 1,000 reais to create one of these systems. So I have been using Linux since 1994, and I've seen things get better. But we can't sit there and just say the CPUs are going to get faster, the memories are going to get bigger, because we still have those problems that we need to have very, very tiny computers and being very, very efficient in electricity so that we can solve really difficult problems that we haven't solved yet. And so for Linux today, All 500 of the fastest computers in the world run Linux. There used to be 2 that ran Microsoft because Microsoft paid them to run Microsoft. But even Microsoft lost out because even Microsoft didn't have enough money to keep their 2 computers in the list of 500. And so recently, all 500 now run Linux. 60% of all the servers in the world run Linux. The rest of them run proprietary systems of different types, and some of them run Microsoft NT. It is the most used operating system in embedded system design. So if you have a Linksys server or a Linksys router, or you have a D-Link router, it could be running Linux or it could be running BSD, another free and open operating system. And it's the basis of Android phones. Now, I don't want to embarrass anybody, but how many of you have Apple phones in the room? Raise your hands, I want to see them. I'm not going to laugh at you, I'm not going to spit on you much. How many of you have Android phones? Yes. And if there's one thing I've learned in 50 years in the computing industry, volume is everything. People will come up to you and say, oh, I'd love to port my application to your operating system, but I need to have this specific compiler, or I need to have this specific thing, and you don't have it. And you say, well, we're shipping 10,000 of these a day. Oh, I was just kidding. We already have it running out of the lab. We can have it, we can announce it tomorrow, honest to God. Volume is everything. And when I was looking at Apple and Microsoft in the mid-1990s, 7% of the market was Apple, 90% was Microsoft, and 3% was everything else. Today, you're going to find that it's moving towards the same model. Apple, I predict, will have 7% of an extremely profitable market. But the rest of the world will be using Linux or free software. Today, 10% of all the desktops shipping or in use or coming into use are Linux-based. That includes Chromebooks and things. I predict that that will increase at the same time that the percentage use of tablets and laptops will decrease because people are using phones more for that. But open source has won. Closed source is in its last gasps, really, because it's too difficult, it's too hard, there's too many different needs for everybody's needs to be met using closed source. And so, if you're going to be programming for the future, you should be going to your universities and going to your high schools and saying to them, you need to use free software to teach computer science. You need to allow your students to be able to look at how the compilers generate the code. Because if you use closed source to teach computer science, you can teach them how to use the operating system, you can teach them how to use the compiler, but they can't see how the compiler or the operating system really works. And that is a problem. There's a lot of things out there which are going on. Field programmable gate arrays, like I talked about, GPUs, they're not just for graphics anymore. And you need to think about all of these different types of things when you're writing your program, even if you're doing them in a virtual machine. We are going into a phase now where the CPUs itself, the actual core, is not going to be getting any faster because we've reached the end of Moore's thing. There's some new technologies which are coming out that might change that a little bit, but we need to get better at creating and being more efficient with our code. We also need to take a look, and particularly in Latin America, about where we're sending our data. Quite frankly, I come from, as I said, from a strange country. We like to look at your sexual pictures that you send through the mail. Our NSA is looking at your pictures, and I don't think you want them to look at your pictures. So I suggest that you start worrying about how to store that data, those pictures, either in places that you really trust, or better yet, in your own home. And there's a series of projects out there, like Freedom Box, which allow you to create a little server that sits in your home, and that's where you can store your most secret and precious of pictures, and your financial data, and other things. We are trying to move towards this. Caninos Lucus is not just about creating small computers here in Brazil. What it's about is creating a completely open operating system and completely open hardware architecture, and that includes a completely open cloud that you can trust and your government can trust. And maybe you don't have the time to go through all of that code to see if there's any trapdoors in there, but your government probably will be looking for those for you. So the side effects of all of this is not just work. The thing is, you can learn a really interesting assembly language, and I don't care which assembly language it is. It could be even PDP-8 assembly language. That's enough. You could learn Intel assembly language or ARM assembly language. Just learn an assembly language. And then learn code analysis techniques that allow you to look at the parts of your code that are used the most. Generate an open source portfolio. As you go through and you take programs and you make them run faster and better and more secure and more stable, keep that in a portfolio. So when you go to your next job, you can show it to people and they'll say, that's impressive, we'll hire you. Take a course in optimization, or if you're a professor, please teach one. And then look at new optimization techniques, digital signal processing chips, FPGAs, and others. There's a series of books and things and algorithms that you should look at. Here are some books. I'll give these slides to the conference developers. You don't have to take notes, so if you want to take a picture, go ahead. And take a look at the ARM assembly language, because it really is interesting. And also RISC-V. RISC-V is coming. RISC-V is going to be here. Take a look at that. That would be a good assembly language to learn. With that, I think I'm out of time, but I'll be here for the rest of the day. You're welcome to ask questions of me. And thank you very much.